Okay, so this is our third presentation on periodic trends, and these are ones that are not in your book. You can find them, they are on the interwebs, but they're not in your book, and we will have problems from active that relate to this. So here we go. We're going to define metallic character, non-metallic character, and melting point. And these types of character relate to the reactivity of the things. We will learn periodic trends for metallic character, non-metallic character, and for melting points. All right, so we're going to take a little detour here, and we're going to talk about Mendeleev's periodic table. Why? Well, chemists started grouping elements by reactivity before they grouped them by atomic structure. So in the late 1800s, they knew 63 elements, and they spent much of their time mixing element A with element B to see what would happen. That was a large portion of the chemical enterprise back in the day. Grouping elements by reactivity, therefore, makes a lot of sense. There were several attempts before Mendeleev to make a table like this, but the reason that Mendeleev is famous is because of the hole in his periodic table. Right there. He predicted that there would be new elements discovered in that hole. And as with many things, people were suspicious, and later, when those elements were actually discovered, Mendeleev's table became ascendant. It was the primary thing that people used. It revolutionized how chemistry was taught because you were able to predict things based on reactivity. Now, this is not the same as the modern periodic table. If you look at the modern periodic table, the elements increase in mass going as you increase Z in general, but not always. Sometimes the most stable isotope has more or fewer neutrons than the surrounding elements, and the trend general and therefore not specific. So Mendeleev's table could not have resulted in the modern periodic table, but the reactivity of these elements that he found trends in is based on the underlying electronic structure. I'm going to say that again. The reactivity of an element is based on the underlying electronic structure. So we'll get a little bit more into it when we talk about the trends. All right, so we're going to start with metallic character. Metallic character is how readily an atom can lose an electron. How easy is it to lose an electron? So you may be thinking, you're a thinking person, you're wondering how that's different from ionization energy. So here goes. Ionization energy is the amount of energy it takes to pull off a mole of electrons from an element. Now, metallic character asks us how fast you can lose an electron. This is an inverse effect. If it takes a small amount of energy to rip off an electron, it is more likely to happen. Therefore, if ionization energy is high, metallic character is low. The trend increases down left. So as you go left to right across the periodic table, this can be conceptualized as being due to ionization energies. But that trend is due to the trend in atomic radii. It is harder to pull an electron off of a smaller atom than a larger one because it is more closely bound to the nucleus and has higher potential energy but lower kinetic energy. So we talked about the lower kinetic energy of electrons in closer orbitals. There's greater potential energy, and you need to overcome the potential energy to pull an electron off. If you want to excite an electron, you need to change the kinetic energy. If you want to remove an electron, you have to overcome potential energy. So as you go down a group, there's a decrease in effective nuclear charge, so you end up with electrons that are loosely bound to the nucleus and easier to remove. So we can explain both why we go down and why we go to the left by using this concept. Now, I said this related to reactivity. So metals are more likely to react with something that needs electrons. So they're less likely to react with, say, water, and they're more likely to react with something that is a cation. All right, so let's talk nonmetallic character. Nonmetallic character is how readily an atom can accept electrons. As is somewhat predictable, this has the opposite trend of metallic character, and the reasoning is similar. Okay, so we go upright from a non-metallic character. And it's easier to add an electron to an atom which has higher effective nuclear charge than to one that has lower effective nuclear charge. In the end, metallic versus non-metallic character is a continuum more than anything else. We make divisions for clarity, but the border of those lines is somewhat ambiguous. So we gave you this like region where you have a different color for metalloids, and we're talking about metallic versus non-metallic character, but in the end, it's a little bit fuzzy. And it's almost always based off of how things react, because in the end, that's what chemists care about. Which brings us to melting points. Materials with stronger bonds have higher melting points. Why? Temperature is proportional to the average kinetic energy. And in order to melt something, you must break bonds. Therefore, if the bond is stronger, a molecule moving at a higher speed, which therefore has higher energy, will be more likely to break the bonds and melt the material. Metals generally have higher melting points than non-metals, so they have stronger bonds. Exceptions to this include beryllium, boron, and carbon. Carbon having the highest melting point of any other element. In addition, metalloids have properties generally between metals and nonmetals for melting point. The reason for this trend can be more fully covered in Chem 108, but as a general rule, metals have higher melting points than nonmetals and metalloids. That's all I intend for you to remember from this. So to summarize, metallic character is how readily an atom can lose an electron. The trend increases down left. Non-metallic character is how readily an atom accepts electrons. The trend increases up right. And for the record, before I forget about it, if we're talking non-metallic character, it is more likely to react with something like water that has electrons that it can give up, because it can accept electrons. And finally, materials with stronger bonds will have higher melting points, so metals have greater melting points than nonmetals, with the exceptions of carbon, lithium, and beryllium. Carbon has the highest melting point of any element.